So in this video, I'll be talking about the Vernier scale, both the linear Vernier scale and rotational Vernier scale as they apply to calipers and micrometers. The Vernier scale itself is used in many instruments. It could also be used in height gauges, other styles of micrometers such as a hole micrometer, a depth micrometer. So it's important to understand how to read them, how to use them, what mistakes to avoid, but some best practices. So I'll be walking through both the linear and the rotational, and that should apply to almost every Vernier gauge that you use. So we're going to start off with the linear Vernier scale. So with any caliper or height gauge, you're going to have the fixed side of the scale which doesn't move, and then you'll have the moving side. And with the moving side, what you're looking for is the zero. You see on the screen here, I've marked off, there's a zero on the bottom and on the top. That's because that caliper has a picture for inside jaws and outside jaws. But on this picture, let's just focus on the outside jaws, which are on the bottom. So you're going to be tracking where that zero mark moves to as it's traveling. And sometimes most times when you're doing a measurement, that zero mark is not going to line up on another line. It's going to line up in between two lines. And that's because you're going to be in between increments. It's just an increment scale. So when you are wanting to find out exactly where you are, you're going to use the Vernier scale to help you. The Vernier scale is basically, the best way to put it, I would say, is it's evenly spaced scales that are at different spaces. And so the scale itself will only line up at one line because they're slightly, the moving scale has a slightly different increment than the fixed scale. They design it such that only one line on the moving scale will line up with something on the fixed scale, which is how you read it. It's almost similar to a slide rule, an engineer's slide rule, similar concept. So just remember, when you're looking at a caliper, we're going to use a caliper as an example. There's going to be a moving scale and a fixed scale, and we're checking where that moving zero goes. So it involves adding a lot of pieces together. So whenever you take in a measurement, you're going to be adding different pieces of what you see on the caliper to get you your final reading. And every piece you add is going to get you closer to the final measurement. So it's almost like you start off with a really close guess, and then you fine tune it until you get to where you want to be. And every piece you add gets you closer. So we're just going to jump right into example. I think it's the best way to learn. So on the top side, the top picture there, to do this reading, we look at where the moving zero stopped. And so we start adding some pieces together. So we're at 1 inch, 0.2, almost, that's very easy to see. So here's the 1 inch, and then 0.2. And then we got to figure out after 0.2, or between 0.2 and 0.3, how far are we exactly? Well, one of the things you need to do when you're reading a Vernier scale, whether it's linear or whether it's rotational, is you're going to be counting how many lines you've passed already. So you have to figure out the increment that is displayed. Every gauge will be different. There's no uniform, whether it's 0.025, like in this example, could be 0.02, could be 0.05. Different gauges use different scales. So in this case, each, between 0.1 and 0.2, there's 4 pieces. So every increment represents 0.025. So that's why in this calculation, I'm adding 0.025. And then that gets you to the final reading. It's 1, oops. Sorry about that. It's 1 plus 0.2, and then the 2 lines I can see, which are right here. I can see 1 and 2. So that gets me to 1.250. Now this is a pretty easy example because the moving zero lined up on exactly on one of the lines. But what happens when it doesn't line up exactly on a line? You could estimate, you could say, yeah, I'm about halfway between two lines, so I'm going to add half of 0.025, or I'm a third of the way, or I'm 9/10 of the way there. You could do that, but the Vernier scale will actually get you an exact reading. So in this bottom example, I've shifted the caliper a little bit, and now we're in between two lines. And so we're going to use the Vernier scale to determine exactly where we are. So over here is the zero, the moving zero that I showed you. And we're going to go through the math again. This is a slightly different example at a different location. So first of all, we see 1 inch easily at 1.1. Okay, here's the 1 inch, 1.1 exactly. Now we're between 1.1 and 1.2. And how many lines have we gone past? Well, we've gone past two lines. Those two lines are here and here. So we're at least 1.150. And then because we're in between the second and the third line, we need to figure out how far are we in between. And so the Vernier scale, the way it works, this moving scale here that goes from 0 to 25, only one of these lines is going to match up exactly with one of the lines on the fixed scale. And it's going to be very difficult to see sometimes because, you can see how small these gauges are. And, your eyesight, you may need good lighting. And it can be tricky. Sometimes two or three might line up. But in this example, I try to take a very clear picture and see if you can tell which of these lines on the bottom from the moving scale lines up exactly. I think this 9th increment lines up perfectly with this number 6. Whichever number or line matches on the top is inconsequential. It does not factor into the calculation. It's just there. It could be any one of these lines. So you might see what I say is maybe start from left to right. You could say no, 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 oh, maybe, 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 no, 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 no. And then you can zoom in on just a small section of what you think might be lined up perfectly and focus your eyes there. So in this case, to add the last piece of it is the 9th line on the scale gets me to 1.159. So this can be very difficult. I'm going to try to show you on the second camera here. So let's do an example. If you have the drawing for the step shaft and you have the part available, why don't you grab that? I've got the drawings for all my parts right here. So I've got the step shaft drawing, and we're going to try to measure this 0.508 diameter right here with our Vernier scale caliper. So let's see if we can do this and show it on the camera. So first of all, with this caliper, this is a metric inch caliper. So this is a different one than I have in the pictures. The bottom scale is metric, the top scale is inch, and the top scale, or actually either scale, works for the inside jaws, the outside jaws, the depth jaw, and the depth bar. If you've watched the caliper video, you know what I'm talking about. So we're only going to focus on the top. We're going to focus on the inch scale. And I'm going to gently close this. And from what I can see, if you can't see it on the TV screen, check out this camera view in front of me right here. That moving zero up here is just a tiny bit past the 5. So I'm at least 0.5. And I have not yet reached the first line, okay? So each line represents 0.025 on this caliper because it's broken up into 4 pieces. Each major increment is broken up into 4 pieces from 0.5 to 0.6. There's 4 sections. So I haven't gotten quite to the first line, so I don't add 25 thousandths for that line. What I'm just going to put 0 lines, and then we're going to add whichever line lines up. So now it becomes tricky. I am scanning my eyes from left to right, and definitely near the 0, near this side, none of these look very close to my naked eye, but it starts to look closer in the middle here, and then the far edge, yeah, it doesn't look very close. And you know what? I'm gonna set this down, lock it, so that I can slide this off. All right, let's get rid of that. Off to the side. Clear off our space so the camera can focus. All right. There we go. And we're going to try to see which of these moving scale, right? The moving scale lines up with the fixed scale. This main beam is the fixed scale. And I'm going to say, let's see. I'm going to say the 13 looks best to my eyes. The 13 or the 14 or the 15 is looking pretty good to me. I'm going to go with the 13. So how does that math work out? So let's grab our whiteboard and put the math together. So starting off with 0.5, I can definitely see 0.5. Lower. 0.500. And then I haven't reached any lines, so I'm not adding any lines. I'll even put 0 lines. And my last Vernier scale increment was 13, so I'll put 0.013. Add all that together, I get 0.513. Okay? And because we're trying out something new with the Vernier scale, let's do a double check with our digital caliper. Try to measure the same area. 5/16. This part actually has quite a bit of error, so I may not be grabbing exactly the same spot. There's a 5/13 spot. Here's a 5/16 spot. So I'm in the ballpark. I haven't been able to duplicate exactly where I grabbed this diameter because it has some error on it. But I didn't make a huge mistake by adding 25 thousandths or forgetting to add 25 thousandths. I'm not that far off between my two calipers. So we could do another example. I'm going to do the largest example. If you're looking at the print, the largest diameter here represents 1.235. So I'll grab our caliper. We'll do a much larger diameter. And let's see what we've got. Looking at the top scale, I've got at least 1.2. And whether or not I've reached that line is going to take some effort. So let's set it down, lock it, slide off the part, and let's do a thorough check on this. Now, here we go. Come on, focus, camera. You can do it. There we go. Now, whether or not I've gotten to that first line, it's going to take some careful examination. So we're gonna see which number lines up. If a number on the right side lines up, it means I haven't quite gotten to the first increment. I'm getting closer, but I haven't quite gotten it. And if a number over on the left side lines up, I'll know I've already passed that first increment, and I just need to add a little bit more to it. So if you accidentally add or subtract an entire increment, that can make a huge effect, so you want to be careful. So from my eyes, I'm scanning from the left, and actually the left side looks pretty good and the right side looks not so good. So if I had to say the moving scale on the top, best that lines up is probably the 3 or the 2. It's not the 4, it's not the 1. I'm going to say it's the 2. I think if you can't see it on the camera here or there, I'm going to say it's the 2. So let's add this example together. Move my chess pieces. Slide you over. So here's our second example. And what do we have? We started off with quite easily, we can see 1.2. Yeah, don't want to make a mistake because I'm looking through a camera. So I'm at 1.200. That's quite easy to see. And now we count how many lines we can see. And I determined a minute ago I can see one line that I've crossed. So I'll put 0.025 for the one line. And then my final Vernier reading was 2 thousandths. That's what I said earlier. Do 0.002. What's that add up to? 1.227. So, because I don't use Vernier calipers every day, I will double check that with digital. Something I encourage you to do whenever you're starting off with a new tool. Okay, I'm in the ballpark. Again, I didn't quite grab the same location, but I didn't add 25 thousandths wrong. Now, in this case, Vernier scale caliper told me 1.227. Digital told me 1.230. If we calibrate each tool and they both pass calibration, that 3 thousandths different is probably down to my eyeball, my grip, maybe the accuracy of the Vernier may not be as good as the digital. Any one of those could be a combination. So Vernier calipers in a small size are just not as popular. You saw why. It takes longer to take a reading. The digitals have really moved past them in terms of accuracy. Well, that's debatable, but in terms of ease of use, and you get great accuracy out of this. Whether one's better than the other is debatable. You know, you can compare the manufacturer specs, but in terms of accuracy, but digitals are very accurate and fast. So Vernier is not something I use every day for that reason, but it is a legitimate gauge to use, Vernier one, if that's what you have available. So we will flip back to our presentation. That's a couple of examples, and you have this other example of pictures here. So as I said, only one of the marks lines up. Let's try. I tried to zoom in as close as I could. The top scale is reading, or the top example is reading 1.000 exactly. I measured a Joe block at 1 inch, and so you can see actually the 0 and the 25 on the top side here line up perfectly, but you wouldn't add 25 thousandths because your moving 0 is right at the 1. Now on the bottom example, it's the same thing, or it's a different thing. I'm a little bit past the 1 on the moving side, or the moving 0. Right here, this is in between a couple of increments, and the 13, I say, lines up perfectly. So hopefully that's clear enough for you guys to see. So yeah, as you saw me struggling, which line lines up, this is kind of what I'm doing in my head. I've got, on the right side, the way this works left to right, I said you're kind of zooming in on what's going on. Here you're somewhere between 0 and you're somewhere between the 1 inch and the first line, but you don't know where. And the 13 is what lined up perfectly right here. And if we blow that up, this is kind of what it looks like, where the 13 lines up perfectly and the line to one side is off just a tiny bit and the line to the other side is off just a tiny bit, and they should be equidistantly off. So only one of them is going to line up. If I bump my moving scale just a hair to the right or a hair to the left, a different set of lines is going to match perfectly. So it can be very hard to see. As you saw me struggling, I always said it could be a couple of these lines that look good. So here are your steps. Again, just as a review, locate your stationary and your moving scale. So stationary won't be moving, moving side, moving scale. Locate the moving zero mark. Determine your spacing. So whether it's 25,000 increments or 20 thousandths or 50 thousandths, whatever it may be. Take your measurement, look at where the zero mark stopped, and then do your math. Count the lines, and then do the Vernier alignment, add everything together to get your final reading. As you get better at this, you'll be doing all 4 steps naturally, instantly. You won't be thinking about it. But for the first month or so, I was doing it. I was sometimes even writing it down just because I didn't want to make a mistake. So linear Vernier scale is a good example, but odds are you won't see it very much in modern manufacturing. You're going to be using digital calipers. You're going to be using dial or digital height gauges. So you may not see the Vernier scale all that often unless you're using some older equipment, which is fine. But newer equipment sold in the Vernier scale is less common than some of the other ones. But the rotational scale, that's a different story. So the rotational scale you're going to see all the time on micrometer instruments. Because that Vernier scale, again, gives you really good accuracy. And that's how micrometers are so accurate. It's part of it is down to, you can read it. It's fine to design like a ball screw and a marking system that gives you really fine control, but if you couldn't read it, you'd end up with the same accuracy as a caliper. But the micrometer actually gives you kind of 2 scales. It gives you one on this rotating thimble, and it gives you a better one, more finely addressed Vernier scale here on the rotational. It gets you down to 10,000th increments instead of 1,000th increments. So it gets very accurate. And the concept is the same. You're just looking at where things line up. So in the micrometer, you kind of have a zero line instead of a zero mark. But you're still going to count lines. You're going to have to determine the spacing, just like with the linear version. So in this example, it's probably a little hard. Sorry about the shadows on the pictures, but try to do my best. In this example, it's reading 0.5917, and how I got there is I can see the 0.5, definitely, right? I can see that 0.5, and I haven't gotten all the way to the 0.6. I can count 1, 2, 3 lines that I can see very clearly. So there's 1, 2, 3 lines, 25 thousandths each, because the spacing is the same as our previous examples, but it's not always. And then how did I get the 16? Well, actually this zero line here and where this thimble lands, this is almost like a Wheel of Fortune wheel. You're landing between the 16 and the 17 on this zero mark. So I'm going to add 16, and then once again I have another situation. I'm between 2 numbers, and I'm actually now between 16 thousandths and 17 thousandths. So we have a scale here that's on the sleeve that gives you another Vernier scale that will tell you exactly where you are. And in this case, I said the 7/10 lined up perfectly. So we're gonna keep going with this example. or we're going to keep going with a few examples so that you can understand a little bit better. So for one thing, you want to pay attention to these two edges, or these two lines. So one of them is the edge of the micrometer sleeve. The micrometer thimble. Basically the moving part. That, wherever that edge is where you're reading, taking the measurement. And then you're also looking for this red line here is helping you determine the sleeve scale. So the steps are basically look at where the edge of the thimble crosses the scale. Note the large number you see. So I see the 0.4, definitely. I don't see the 0.5 yet. Add how many small lines you can see. Step 3. So I can see 2 lines. Again, 1, 2, I can see very clearly. So 25,000 each. Then step 4, add the number of lines. Add the number that lines up with the scale center line. So that's my best way of saying the 14 is the number that lined up with the scale center line. And in this example, again, it lined up perfectly. So I ended up with 0.4 plus the 2 lines I see plus the 14, 0.464. Okay? And just like our linear scale, you got to ask yourself what happens. Like in this example, this first example, what happens when it lines up between 2 numbers? Okay? What happens if it lined up between, say, the 14 and the 15? Well, I'm at least 0.464, and then what additional movement did I get? So you could either estimate it, but if you have a Vernier scale on your micrometer, you can go ahead and use it. So how does that work? We'll jump back into our 5917 example again. And so I already talked about 0.5, 3 lines, 16ths, and 7/10. Well, let's take a look at where that 7/10 came from. If you on an OD micrometer, if you look at the sleeve, if you just rotate it and you're not looking at the main scale anymore, you're looking at the sleeve scale, you're going to look for where these numbers line up, just like on the linear example that I gave you. So in this side, there's a number, there's basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 scale right here. And this is the number that you're looking to line up with. So one of these 11 numbers, or 10 numbers, is going to line up exactly with a line over here on the rotational side. And the number that is over here is inconsequential. This is not the one you're using for the math. You're using this number for your calculation. So remember that. And you're just looking up for which one lines up. And it helps to kind of rotate, because it's the only way to do it is to get a direct reading straight on to see which one lines up. So in this case, again, this is the same example. I think the 7 over here lines up perfectly with this line. So the left side is what I'm going to add to my measurement. So I got 0.591. From these first 3 steps, I end up with 0.591. And then the 7/10 here gets me to 0.5917. And what's going on, if I kind of took that big micrometer and just shrunk it, that's all that's happening here. The 7 is lined up perfectly with this number 1 over here, and then the spacing of the other ones is off just a little bit, so that if I ended up rotating the sleeve, this sleeve is the part that moves. If I ended up rotating that up or down, a different number would line up perfectly. But in this case, it's the 7 and the 1 that line up, and I use the 7 in the calculation, and the 1 doesn't matter at all. So before we do a live example together, let us measure some parts. So we're going to keep going. This was a 508 diameter on the tip, so I'm going to measure that with the the micrometer now. I've already done it with the linear. And go ahead and check out my micrometer video to learn about how to use a micrometer, but we're just going to focus on reading the scale. Alright, so I got decent. Slide you out, and let's take a look at what we've got. So I'm at least 0.5. Okay, that's easy to see. And I don't see any lines, right? I don't see a hash mark past the 0.5. So I'm between 0.5 and 0.502, sorry, 0.525. Between 0.5 and 0.525. And to me, man, it looks like the 17 lines up perfectly. And if I go to my rotational scale, look at that. The 0 happens to line up perfectly, and the 1 doesn't, the 2 doesn't, none of these other ones line up perfectly. And when I get back to this other side, yeah, the 0 lines up perfectly again. So this is actually an example where I got exactly 0.517 with no 10th increment addition. 0.5170 would be my final number. We'll do another example. We'll do the big diameter again. The big diameter is 1.235. The odds of this happening twice, I think, are fairly low. So this time we should end up between two numbers. So again, here we go. Slide that off, close this up, lock it down. All right, let's see what we've got. All right, now we are between two numbers. We're at least 1.2, okay? Because this is a 0 to 1 micrometer, we're already starting at an inch. So we're at least 1.2, and I can see one line. So we're at 1.25, and then we're between a 5 and a 6. So we're at 1.30. Sorry, 1.230. And then how far between 5 and 6 are we? We are, which one lines up good? The 9 doesn't really look like it. Well, none of these look better than the 9, right? I'm rotating around. I'm looking at this side. None of these really look all that good on the low end. And the high end, yeah, let's say the 9. And the 9 and the 17 look the closest to line up. So how does that math work? Pull out our whiteboard. Let's do the math. So we're at least 1.2 and one line. So 1.200. 0.025. That's my one line I can see. On the thimble, I'm between the 5 and the 6, so I'm going to pick the lower number and add the 5. And because I haven't quite reached the 6 yet, but on my thimble scale, the 9 lines up. Sorry, on my sleeve scale, the 9 lines up perfectly, or almost perfectly. So that's what I'm going to add here. So what I end up with is 9, 0, 3, 2, 1.2, ooh, sorry, didn't realize you couldn't see that. 1.2025, 5,000s, and 9,000. These are all the pieces that I added to get to 1.2309, which is what we got, pretty close to what we got with the caliper earlier, right? We got about 1.233 or 230. But since I can't remember, let's double check. Yeah, so we're close with our digital. 9/10ths different. Caliper is not capable of 10th scale. It's only going to show you 3 decimal places and not 4. So the micrometer gives you a little bit of extra accuracy and resolution. So let's flip back to our presentation example. So how about this one? Let's try to do this together. I'll talk it out loud. If you're not going to use the thimble or the Vernier scale to help you determine what this number is, what do we think? So we've got 0.3 and I can see 2 lines. But I don't know the rest of it, right? I don't have a thimble scale to guess and I don't have Vernier scale to guess. So I'm going to guess 0.365. And that's what I thought it is. That's what I think it is when I look at it this way. If I black out what's there. And then we start taking a look at reading what we actually have. So I got my 0.3 and I got my 2 lines. But now I can see on the thimble, I'm between the 11 and the 12. So that gets me to 0.361. And then when I rotate around and I take a look at which sleeve increment lines up with the thimble, I get the 1 on the left side. The 1 lines up, so I get to 0.3611. So hopefully, if you didn't get that example, keep practicing. And if you have to do 30 in a row, it'll be worth it to spend an hour practicing. Because once you get it down, it'll be easy. But if you're still struggling with it, you're still rusty, you don't want to make a mistake. Because if you're busting this out, if you're using this tool, you're probably doing something that's very tight, precision, very small tolerance zone. That's when you use this instead of a caliper. So if you make a mistake, you don't have a big window to make a mistake. You could really mess things up. So and double check yourselves with the calipers just to make sure you're adding your math and you're getting reasonably close. All right, so I've already kind of talked about some tricky reading the scale, seeing which one lines up. One of the errors that is prone for Vernier scale, whether it's a micrometer or a caliper, we call it alignment error. And basically this is when you think 2 lines are collinear and they're not. Or even sometimes 2 lines should be collinear and they're not because of a calibration issue. So it could be, like I said, it could be calibration, it could be chips, you could be grabbing a chip on the part. It could be that form error. When we measured this smallest diameter, I mentioned there's a lot of taper, there's a lot of form error in this diameter where I got like 3 or 4 thousandths different no matter where, different places I was checking it. So that could be one of the reasons. Taper, flatness, parallelism, that might be it. But either way, do your best to try to minimize this alignment error with good practices, good amounts of pressure, holding everything perpendicular and parallel when you're making your measurements. Nothing's at a weird angle. And so if you have good technique, you're going to minimize all this problem. And don't be afraid, like I did, to lock down. Use the micrometer lock. Slide off the micrometer from the part and really get it up close and take a look. Bring out a loop, a magnifying glass if you need to. But it's really important to get this right. And then I'm going to take a little detour. I've got the dial caliper here. And I just want to point out that a dial caliper is not really a Vernier scale. Not in the same sense as these other 2 gauges that we looked at. It's much easier to read a dial caliper. It's almost the same concept. You look at where the main scale crosses. So the main scale is going to end up between 2 numbers, just like anything else. And then your dial is going to zoom in exactly where you are. And it's pretty much going to do it in one step. Not multiple steps. There won't be lines to count usually. There won't be Vernier scales to calculate or Vernier scales to match. So this dial in the picture and the one I'm holding goes from 0 to 100, and that increment is a thousandth of an inch. So a full rotation is 0.1 of an inch, and that matches exactly my fixed scale. Each line is 0.1 of an inch. So because they're even, it's pretty much a direct reading. In this example, you land between the, well, the number example doesn't match the the picture, but in the bottom example, 0.3 and 45 becomes 0.345. That's a very quick calculation. So let's repeat what we did a couple times with our dial caliper just to illustrate the point. So one more time, and then I can kind of read this very quickly. Right here, this is where I'm reading. It's past 0.5, it's not to 0.6. How far past 0.5? Looks like 18 thousandths, so 0.518. It's that simple, just two numbers to add together. Close to what I got with the visual, right? So we do the big diameter. There's 1.2, and I'm between 1.2 and 1.3. And how far? I'm pretty much dead on 30, 1.230. And that is consistent with what we've gotten with our other tools. So it's a little easier to use a dial. The dials have really become more popular than the verniers. First is digital. Those tend to be most popular. Then the dials. They're a little less expensive and still give you great resolution. You can even kind of estimate in between lines. There's no additional scale, right? There's no additional scale to actually tell you how far in between two numbers you are. Oops. But you can still estimate it. If I could actually bump it off of a line, you could still estimate, yeah, maybe you're 8. I mean, and that's fine. It's better than not estimating it. You can, if you remember from high school chemistry classes, I remember at least, they said, if something lines up between two lines and you don't have a scale to tell you exactly, go ahead and do your best guess, because you're going to do better than just rounding that to the lower number or rounding it up to the higher number. Do your best guess to add one more decimal point of accuracy that you can see. That's not always allowable in metrology, but it's more of a... There are some situations where it makes sense. There's some situations where it don't, and I can't really give you too many examples of either one, but throughout your career, you're gonna run into situations where it's like, yeah, I can estimate this fairly accurately and do a better job at rounding it off. So let's jump back and kind of wrap things up. We're almost done here. All right. So I want to thank you guys. Oh, we are done. I want to thank you guys for watching this video. I hope you learned something about the Vernier scale, both the rotational and the linear. Very important for you to understand. As a machinist or an inspector, you will see this, and you don't want to be caught off guard when you need to use it on something critical. Especially the rotational scale. One more thing before I sign off, I'll show you some examples of other rotational scales. This is a whole micrometer, and one thing you might notice, how many lines are in between increments. So let's go from the 0 to the 1. Well, there's actually 4 lines, which means it's divided into 5 parts. So this is a micrometer that has a different scale increment than we were working with on our OD mic. This whole mic has a different increment, and if I open this up a little bit and rotate it around, you'll see there's no Vernier scale to help us determine exactly where we are whenever we line up between two lines. So the reason for that on this scale, for one thing, each line is 2 10,000ths. And on this, the Vernier scale resolution was 1 10,000th. So there's not a huge difference. And so this is giving you pretty much a direct reading without the need for a Vernier scale, you can just check out which one lines up. There's no amplification and matching that was necessary with our other gauge, with our OD mic. So this one's going to be a little bit easier to read, but you don't get quite as fine a resolution. But as I just mentioned, if I end up between two lines, well, yeah, I know they're so small, and each line is 2/10,000ths of an inch. So if I end up between, that's basically 1,000th of an inch that you can add or subtract with, depending on how you're thinking in your head, whether you're going above or below. But either way, that's a great time where you can estimate how far you've gone between two lines. But really, the resolution of this is so fine that it gives you almost a direct reading. And then we'll talk about this depth micrometer. When I open this up, and it's almost just like our OD micrometer. I have the scale here. One thing you'll notice, the numbers are counting backwards, right? The numbers are different than before. Let me line up the 0 just to illustrate the thimble. So on our hold on, let me give me a second to really illustrate this one. So on our depth micrometer on top, it starts 09876, and then our OD mic goes 0123455. And if you look at the thimbles on both, the 0, there's a, it's going 20 to 0, and here it's going 5 to 0. All right, can you see that pretty much everything's backwards between these two? Because the way you use a depth micrometer, the way you read a depth micrometer, fundamentally different to how you do an OD mic. So you got to pay attention to that and know that. Just know what you're reading. So one other thing, if you see this and I rotate it around, it also has no additional Vernier scale resolution. So this is only going to give you 1,000th resolution, and you can basically guess that 10,000th because you don't have any other choice. There's nothing else here. Otherwise, it's going to, how do I say this? If you round it off, you're going to be losing some accuracy that you can determine without a scale. So that's a couple of different examples. You got to look at every gauge you're using and figure it out. Every once in a while I come across a new gauge that has a new style that I haven't seen before. I'm like, ooh, okay, I almost made a mistake here. So let me jump back into the thank you. Thank you again. Please check out my website, pragmaticmetrology.com, for more of these training videos, more resources, and I want to thank, I really need to thank the Laney College in Oakland, California, for providing parts and tools for me to use in this videos. They provided this part, and they provided many of the tools that I've been demonstrating, like the micrometers. And the college, the machine technology department, has a really great program for learning about CNC machining and manual machining, metrology, inspection, quality control, CMMs, CAD modeling, mechanical systems and drives, and pump shafts, and all many great skills. So please check them out. They've got a lot of classes, certificate programs, associate's degree, and apprenticeships that they have to offer. They're in contact with local companies, so it's a great way to advance your career, meet some people that are also in this industry. And so please check out Laney College in Oakland in the Northern California Bay Area if you are there and you're watching these videos. And please check out my website for more of these training videos. And thank you, and I'll see you next time.